Welcome to our next video in the series on condensed matter theory. In this video I would like to talk about the Hartree equation and show that we can derive this by a variational principle from a wave function that is just a product wave function of the one particle states and thereby violates the Pauli principle. And when we look at the variational derivation, we're going to calculate the energy when we vary our wave function. And we know that the ground state wave function of our full many-body wave function is the energy that is the lowest. So when we vary our wave function over all possible wave functions, then that wave function with the lowest energy, so an extremum in the energy landscape, is going to give you the correct eigenstate for the ground state. So we know that if we look at eigenstates of our Hamiltonian, then these eigenstates span a complete orthonormal set, and we can order the energies of our eigenstates such that Ei is smaller or equal than Ej when I is smaller than j. And we also know that the ground state has a lower bound, at least in the Schrödinger equation. When you go to the Dirac equation, there was a problem with the lower bound, and that has to be solved in a different way. So, based on these considerations, we can write down a general wave function as a sum over all eigenstates. The eigenstates form a complete orthonormal basis set, which means if we calculate the energy or the expectation value of our energy of this arbitrary wave function, then it is a sum over the norm square of alpha I times the eigenenergy of that eigenstate I, and this is always equal or larger than to the ground state energy. Actually, it's only the ground state energy when either states are degenerate or you just sum over those states that have the ground state energy. So alpha I is 1 for I is 0 and 0 for all the others. So we know that our ground state wave function is the state with lowest energy. With a constraint that the norm of our wave function is equal to 1. So what we have to do is we have to minimize the expectation value of the Hamiltonian as we vary our wave function. And we can either vary the bra or the get wave function. You can vary the real and the imaginary part of your wave function, or the wave function and its complex conjugated. So we are able to treat psi and in bra and ket as different states when we do the variation. Well, if you minimize the value of a function, or in this case a functional, because for different functions we give this a real value, then we can look at the functional derivatives. And if we vary our wave function and look at the expectation value of some operator, then here we vary the ket factor, and as a result, if you take the derivative of x with respect to x, then it's just 1. So if you take the derivative of a get with respect to a get, then it is just 1. And what we have here is psi times the operator. And the same we can do, but now the derivation with respect to the bra, and that gives you O psi. So we want to minimize our energy, which means we can look at the derivative of the expectation value of the Hamiltonian and require that this is 0. So this is a needed condition, but it's not, so not all states that follow this condition will be the ground state, but the ground state will follow this condition. Now this is not sufficient because we are not looking at any state that is minimizing the expectation value, but we have a constraint, and we can add those constraints with the use of Lagrange theorem, where we add a Lagrangian multiplier and say that this now has to be fulfilled for some value of lambda. So we can show that indeed an eigenstate fulfills this condition. So for an eigenstate we know that H psi is E psi, and therefore the derivative here is given by E minus lambda times the inner product of a wave function, and this has to be 0, which means that either lambda is equal to the eigenenergy or our wave function is 0. This is a necessary condition, not a sufficient condition, so we see we do find solutions that are obviously not the solution we're after. But when we find the solution of this equation where lambda is equal to the energy, then we have a minimum. Now we can look at the Hartree approximation. And we can derive the Hartree approximation by assuming that psi is not a general wave function, but that psi is a wave function R1 up to Rn that we can write as a product of one particle states up to psi n Rn, or a product I is 1 to n phi I Ri for some sets of functions I. That are orthonormal. Phi I, phi j is delta ij. So that's the claim that I make, and will prove later that if we write down a wave function in this form and find the minimum energy of all wave functions that can be written in this form under the constraint that my one particle orbitals are orthonormal, then I will come back to the Hartree approximation. Well, and this of course violates the Pauli principle. Because we assume here that we write down a wave function that is not antisymmetrized. Now let me prove to you that the wave function that can be written down as this with minimum energy gives rise to the Hartree equations. And for that we're gonna say I have my H1 acting on particle I as the kinetic energy of particle I plus the Coulomb energy of particle I with the lattice as well as E square Zj Ri minus Rj as well as the energy that we have between all nuclei which I now have to equally distribute between all electrons. And we have our two-particle interaction, which is given by the Coulomb interaction between our electrons, 4 pi epsilon 0 E square over Ri minus Rj. And our Hartree energy can be calculated from this, which is a sum over all electrons, phi I, Ri, Hi1, phi I, Ri, plus a half I is not equal to J, phi I R1 Ri, phi J Rj, Hij2, phi I Ri, phi J Rj. We have to make one warning. We write down here bracket states. We've done this before in second quantization. So if I create particle 1 and particle 2 out of the vacuum, then this is a state that is fully antisymmetric. So that represents the wave function psi1 R1, psi2 R2 minus psi2 R1, psi1 R2, and that is not equal to the wave functions that we write down here because we are not antisymmetrizing R1, psi2 R2. In many cases we do not include the coordinates in our wave functions when we write them down. And when people write down a wave function like this, instead of in second quantization, you have to be a bit careful which wave function they mean, the fully antisymmetric or the not antisymmetric one. But in many cases, people will mean the fully antisymmetric one, because this is the state that makes physical sense. And then you can also write this as psi1, psi2. Good, that as a side note. We are not talking about fully antisymmetric states here. So we have to minimize the Hartree energy with the constraint that the dot product of our one particle orbitals that we use to generate the Hartree state is 1. For that we can look at the functional derivative with respect to a bra, and I'm taking the derivative with respect to the bra psi m of the Hartree energy minus the sum over all one particle orbitals lambda psi I Ri psi I Ri. and this has to be 0. We can use that if I take the functional derivative with respect to a state of a sum over all one-particle states, then this is just a delta function Im. If I take the derivative of x plus y plus z with respect to x, then it's just the x that is going to remain. Or if I take the derivative with respect to a variable m, then this is the mth variable of a sum over all variables, then it's the mth variable that will remain. So if we now take that partial derivative or that functional derivative of the Hartree energy, then we first of all find that we have our h1 term in there. So this is the one particle Hamiltonian acting on state m. And we have here the derivative, which gives me the delta function between I and m, Rm, plus, and now we have to take the derivative of the second term, and we can either have I equal to m or j equal to m, so that's going to give me two terms in there, a half, and we assume now that I is equal to m, so then we have j is not equal to m, and we have phi j rj left, h mj, 2 phi j rj, and then the get for psi m. The derivative of the bra became a delta function, so all i's are replaced by m's and the j's remained. And we can do the same, but now take the derivative of psi j, so then we have I is not equal to m, psi I ri, h I m, 2 psi I ri, phi m rm. And this has to be equal to or lambda times psi m. So what we have left here is an eigenvalue equation, h1 plus this term plus that term times our wave function is lambda times the wave function. So we find that we have an Hartree Hamiltonian that is given by h1 plus 1 over 4 pi epsilon 0, the sum over all occupied states, phi I ri, e square rm minus ri, and then psi I ri. And this is exactly the Hamiltonian that we had also in the previous derivation for the Hartree approximation. We find that the kinetic energy is unchanged, as well as the interaction between the atoms or the electrons and the nuclei. And the Coulomb repulsion is replaced by an interaction with the charge density and then an integral over e square r minus r prime when we have the charge density at r prime. So this is exactly the Hartree approximation that we used before. Which means that when we derive the Hartree approximation, we are looking actually at these states that can be written as a product state and then the lowest energy of that state. And that violates the Pauli principle because those states are not antisymmetric. This we will repair within the Hartree approximation, and that we will do in the next video. Thank you very much for your attention. Stay healthy.